All right, it's time to begin Chapter 9, which is Solids, Liquids, and Gases. Now, we've kind of already touched a little bit on the nature of matter in the previous chapter, and now we're going to expand upon that a little bit more. So, solids, liquids, and gases are all what we call states of matter. They're sort of the way the atoms and molecules of a certain type of whatever are organized. So when they're solid, they're all stuck together in some sort of maybe lattice, but they're stuck. That doesn't mean they can't move. As we talked in temperature, those things stuck together still wiggle back and forth, and how fast they wiggle is a reflection of their temperature. Well, then they can also be liquid, where they're kind of stuck together, but they can break apart, come back together, and they sort of flow. They fill up whatever container they're in, but they're not necessarily fixed. They're kind of loosely hanging on together. And again, how much they wiggle, how fast they're moving, is a reflection of their temperature or how much energy they have. And then our other most energetic form of matter is gases, where they're no longer stuck together at all. They're completely free to zip around and move. And again, how fast they're moving around, their average velocity, or root mean square velocity technically, is a reflection of what their temperature is or how much energy they have. So starting off, let's just list the states of matter. Now I've highlighted the ones that we're going to focus on, solids, liquids, and gases, but there's actually a couple more, and I usually leave this as an open question to the class, but obviously you guys can't answer me. So I've listed the two more common, still incredibly rare, states of matter, and that is Bose-Einstein condensates and plasmas. I'm not going to really expound on that at all, but if you guys are curious, if you're bored sitting at home, which I know most of you probably are, give Wikipedia a look, learn a little bit more about these rare states of matter. But as I've organized these, they are low energy at the top, higher energy at the bottom. So the lowest energy would be those Bose-Einstein condensates, but then getting into more common states of matter, solids are the lowest energy, liquids are sort of medium energy, and gases are high energy. And then of course beyond that is plasmas. But what the whole point of this chapter is really how do these various states of matter, how do solids, liquids, and gases behave when we push on them or change their temperature, when we apply forces to them, or whenever we change the amount of internal energy they have, change their temperature. We're going to start with solids. So for solids, we'll start with pushing and pulling. Some solids are what we call malleable. An example of this would be gold. That means that it can be bent into things like jewelry. You can push on it and it bends. Well, another property of some objects is ductile. Some things are what we would call ductile or ductile. Ductile things, for example copper, can be stretched out. You can pull them without them breaking, and it can be stretched out into things like wires. This is why we use copper as wiring. It's also a good conductor. Those combinations make copper an ideal material for making wires. But what if we took this even further? If you push or pull hard enough on an object, eventually it's going to break. And we have special names for all the ways in which things break. So, first off, let's talk about shear strength. Shear strength is breaking across a bar. If I push upward on one side of the pen and downward on the other side, eventually it would break, and the amount of force necessary to break it in that fashion, pushing on one side and pushing on the other side in the opposite direction, that is what we would call the shear strength of the material. Another type of strength is tensile strength, or the stretching strength. It's the maximum tension that an object can can support before it breaks. We see this a lot with things like fishing line or any type of rope or chain often has a tensile strength. It's how much you can pull it before it breaks. And so yeah, fishing line's the most common one. You guys can probably come up with other examples, but there's usually pound limits. Well, we know pounds are a measure of force. That is how much force the fishing line can withstand before it breaks. And I love tensile strength because there's a great video, or really a song, I guess, from the cartoon Blaze and the Monster Machines that my son likes to watch. And Tensile Strength has one of the best songs in the entire show. If I can track down a link, I'll share that as well. But I can't help but sing the Tensile Strength song in my head whenever I start talking about it. The last of these ways to break things is compressive strength. Now, compressive strength is resisting fracture by pushing together. It's usually the strongest, and then you can see this if you look around in the way that things are engineered. If you push on either side of it, you would eventually crush it or crumble it. But that's going to take quite a bit of force. The example I like to turn to immediately with this is the way we build roads. We like to have roads on the ground. Well, that's because you or your car is on top of the road pushing down. Well, there's the ground then pushing back up. And it's very strong. The road rarely breaks. But say something comes like a flood and washes out under the road. Well, if the road is washed out, it's easier to break. We end up with a situation more like the shear strength, where there's something pushing down, something pushing up, and the road starts to break. That's sort of my classic example of why compressive strength is very good, shear strength, not so good. Think about columns holding up, buildings. The structural support of a house utilizes compressive strength. You don't want to rely on shear strength. Sometimes you have to, but that is not ideal. Compressive strength is going to be the strongest way to build something. All right, so that covers what happens when you push or pull on a solid. Now let's talk about changing the temperature of a solid. What happens if you change the temperature of a solid? Well, put simply, it expands or contracts. If you heat it up, it expands. If you cool it down, it contracts. And you can find evidence of this all around you in the world as well. If you're ever driving on the highway, you might notice there's sort of these grids, these teeth-like objects, or sometimes just linear gaps with spaces between them every so often along chunks of road. And that's because the road sits out there in the sun and gets hot and it expands. And then at nighttime it cools down, or in the winter it cools down, it contracts. So the roads actually expand and contract. There's a homework question about expansion joints in windows and why those might be necessary. Well, different objects expand and contract in different ways. And that's defined by this equation here. This is our equation for linear expansion in a straight line. And as you read it side to side, it sort of tells the story. Delta L, the change in L, or the change in the length, is equal to alpha, which is a constant, times the original length, times the change in temperature. So really, you get some amount of change in length from some amount of change in temperature. But of course, it's different for every type of object. That's what this alpha is. This is the Greek letter alpha. It's a constant that depends on the material. It's called the coefficient of linear expansion. And you can look up a list of these on the internet, or if you have practical physics, it's on page 172. Or if you have the college physics from OpenStax, you can go to table 13.2 and look at how different objects expand when you heat them up. But this equation is fairly straightforward to use. Just as usual, remember that delta means final minus initial. So make sure to do final length minus initial length, final temperature minus initial temperature. And you'll see that if the change in temperature is negative, that is if the temperature goes down, you get a negative change in length, that the length actually shrinks And similarly, if that change in temperature is positive, you get a positive change in the length. Something expands whenever it's heated up. And this is the equation for change in length. There's a similar one for volume expansion, and it works the exact same way. You get a change in volume that is based on some constant, that's beta, that's supposed to kind of look like a fancy letter B. It's the Greek letter for B, beta. Again, you can look up on page either 174, 13.2, or table 13.2 in the alternative textbook. But these things are just looked up in a table. They're different for every type of material. So we have the coefficient of volume expansion, however much volume there initially was, and the change in temperature. So you get a positive change in temperature, you get an increase in the volume. You have a negative change in temperature, you get a decrease in the volume, a negative change in volume. So that is how solids behave when we push or pull on them, whenever we change their energy, the amount of internal energy they have reflected by their temperature. And it actually turns out that this expansion and contraction is the same for liquids as well, which sort of gives us a head start on the next section of this chapter. So we've now talked about how solids behave when we push or pull on them or change their temperature. Next, we're going to turn to liquids, but it turns out we've already done half of it. Liquids expand and contract with these same equations. Again, you would look up the alphas or betas based on linear or volume expansion. And you can predict how much liquids are going to expand when you change their temperature. And of course, that means you can easily measure in a straight line temperature change, which is how a thermometer works. This is the old mercury-based thermometers. You have them at some original temperature. You change that temperature, the liquid inside rises or falls. And there's increments marked off to measure that. So that's the first part of our Chapter 9 lectures. So I'll go ahead and pause there, and our next video we will focus on how liquids behave when we push on them.